I'd like to introduce Ravi Naik. He's one of our postdocs and is going to talk to you about quantum processors.
All right. Hello, everyone. I'm Ravi, as Sarah introduced, a postdoc here, Berkeley, and along with Castra, I'll do a two-part talk describing the processors that we have. I'll be focusing on the quantum processors that we're using and developing and their capabilities and performance. Following me, Castra will describe the infrastructure around these processors. So to start out, I'll introduce the device that we're using for many of our current experiments, which you will hear about later, which is this 8-qubit chip. It consists of 8 fixed frequency transmon qubits in a ring geometry. The transmon qubits are coupled to each other, to their nearest neighbors, mediated by a resonator. And in the center of the chip, you'll see a multiplex readout bus, and that enables us to do high fidelity readout with a broadband traveling wave parametric amplifier, or TUPA, you may have heard of. And in the following slides, I'll outline the performance of this particular device. To start out, I'll start with something that is central to the performance of any quantum processor, which is the coherence times of the constituent qubits. Here, I show the average coherence times on our latest 8-qubit sample compared to several commercially available cloud devices. You can see that coherence times T1 and T2 measured with a spin echo experiment exceeding 100 microseconds average across the chip. These coherence times were achieved after years of careful iteration and refinement of the fabrication process, as well as consideration of the microwave environment and packaging, which Castra will touch on. Now, these are very good coherence times, state-of-the-art for superconducting processors using transmon qubits, but further improvements to the coherence times will be required, and a strong focus of our efforts are going into materials characterizations of the surface and interfaces of the devices to determine the remaining sources of loss. Now that we've achieved such high coherence times, we can go to another key part of these quantum processors, namely, how do we manipulate them? And here I'll focus on the 2 qubit gates that we use in these processors, namely the cross-resonance gates. First, I want to start off with a brief introduction of what is a cross-resonance gate and how does it enable us to perform entanglement on qubits. And to do so, let's consider a simple system where we have 2 linear oscillators coupled to each other with a coupling strength G. I've labeled the oscillators C and T for control and target respectively, and you'll see that this is a very suggestive labeling. And what I want to focus on is what happens when we apply drives to the control qubit, and what happens to the target qubit as a result. Well, from the perspective of the target qubit, the control qubit is essentially a filter centered around the control qubit frequency. And if we apply a tone, essentially shake this oscillator, we see that the amplitude that is transferred to the target, if we apply the oscillation at omega t, is reduced by this filter. And if we consider the target oscillator to in fact be a qubit, applying some amplitude at its resonance frequency will result in what are known as Ravi oscillations, essentially flops between the ground and excited state of the qubit. Now, let's take the control oscillator to, instead of being linear, to actually be nonlinear. And by that, I mean that its resonance frequency changes when it changes its state. In that case, if you apply the same amplitude tone at omega t to the control oscillator, the filter function due to the control oscillator actually shifts, resulting in a different amplitude of oscillation applied to the target qubit. Now, if we apply a different amplitude of tone, then we get a different Ravi oscillation rate, as shown here. Now, if we choose the time that we apply this drive carefully, then we can actually perform a C-NOT gate. And this is essentially a very simple picture for how a cross-resonance gate will work. And what this shows us is that there are several key parameters determining the performance of these gates, and we are investigating these parameters thoroughly. What I want to focus on here is that a very important parameter in our system is the frequency arrangement of these qubits. And since we have fixed frequency qubits, this is all defined by our fabrication process. That makes it very, very important that we have a very tight control on what exact frequencies we create our qubits to be at. Here, I am showing data from a study that published this year, where we show systematic improvement in the yield and the uniformity of junctions that we produce. These are statistics made from a 4-inch wafer. And we see that we can improve all the way from a 30% variation in the critical current of the junctions all the way down to 3.4% over the entire wafer. And if we focus on area that is 1 by 1 centimeter, which is the size of our quantum processor, we see that we can reduce that to even lower quantity of 1.3% critical current. And to translate this into units of frequency, if we have a qubit with a frequency of 5.5 gigahertz, this results in a 35 megahertz standard deviation across the chip, a very tight bound for samples. And this is important, namely when we design the qubit frequencies for our cross-resonance gate, as I showed, the exact frequencies are very, very important for determining the performance of the gate. And we see that we, from the systematic improvement, we are able to really tightly define the dispersion for our features, and this results in a 10 times improvement of yield for yielding a desired arrangement of qubit frequencies in our single fabrication run. Now that we've been able to very tightly define the resonance frequencies of our qubits, we're able to perform very high fidelity cross-resonance gates. Here I show data looking at the fluctuations of randomized benchmarking data for one of our cross-resonance gates. And we see that on average, we can get a gate error that is less than 1 times 10 to the minus 2, or 1%. And so we can produce very, very high fidelity cross-resonance gates. Now, this is, again, not enough, and so we're looking more into what are the remaining errors that we have in our system, and what do we need to do to improve them. Along those lines, what I will touch upon is how we diagnose the errors in our cross-resonance gates and how we can go about correcting them. And for this, we use a tool that that is very important for our Q-tree experiments that Alexei and Mikhail will talk about later. But in this case, the high fidelity Q-tree readout will actually enable us to do measurement of leakage outside of the computational subspace. And in fact, if we perform leakage randomized benchmarking, we see that for our cross-resonance gates, the primary leakage channel is actually on the control qubit while we perform the gate. And upon noticing this, we've been employing mitigation of this leakage using targeted pulse shaping, namely a sophisticated drag protocol that is appropriate for the cross-resonance gate. And we've shown a systematic reduction in leakage for a number of tuned gate times. And moving from here, we have now reduced the leakage in our system, and now we need to correct the errors within our computational subspace. But even beyond this, we've worked on providing a multi-qubit context for benchmarking our gates. Namely, we've been able to reconstruct specific error syndromes using cycle benchmarking, as shown in this plot here, which maps out the errors for 3 different gates in a 4-qubit subset of our sample. And this plot was made using software from Quantum Benchmark. This gives us the ability to monitor and correct errors, not just on the qubits that are participating in the gate, but also on spectator qubits in our system. And finally, this gives us a realistic assessment of the algorithmic performance of our processor under randomized compiling, something you'll hear about later from Malcolm. And before I hand off to Kasra, I just want to quickly touch on one other type of processor that we are developing, namely a processor that uses parametric gates enabled by a tunable coupler. Quickly, the gate works as follows. We apply a microwave tone to a flux tunable coupler between 2 of our qubits. The tone is applied at the detuning between the qubits, and this enables a swap type operation. In fact, it is more sophisticated than that. It enables a whole class of gates known as fermionic simulation gates that you may have heard of from Google. From simulation, we've seen that we can balance sort of the coherent errors that we expect and also our decoherence to produce, with even simple pulses, error rates as low as 10 to the minus 3. And currently we have finished design of the sample and hope to fabricate it once capabilities open up again. And now I'll turn it off to Kasra.
All right, thank you, Ravi. I'm ready to share whenever you stop sharing.
I'll stop sharing.
All right. Thanks again, Ravi. So my name is Kasra Norouzi. I'm a postdoc at LBL working on the Advanced Quantum Testbed. And today I'm going to talk about the hardware infrastructure of the AQT that supports experiments and chip development like the ones that Ravi talked about. So starting with the overview here, of course, we deal with superconducting qubits. And so at the core of the facility, we have a 1 milliwatt dilution fridge. And I will talk about the cryopackaging, housing the quantum processors in the fridge, and the cold stage, which organizes and partitions the experimental space to accommodate multiple experiments in parallel. To control the superconducting qubits, we use RF waveform generators and analyzers, both from commercial providers as well as our own parallel in-house development to meet the custom needs of our researchers and users in the future. And of course, very central to the theme of the Advanced Quantum Testbed is all of the collaboration that we have at LBL with, for example, UC Berkeley, Bleximo, which is a startup incubated at LBL with whom we work very closely, and our colleagues at MIT Lincoln Lab as well. And I will try to touch upon some of these collaborations pertaining to the hardware development efforts as I go through the slides. So starting at the very bottom of the fridge is the cryopackaging. So this is where the quantum processors, such as the one that Ravi talked about, is housed. The quantum processor is typically wire bonded to the PCB that sits inside a box that interfaces using connectors to the outside world, to the fridge, and then the controls equipment. So on the left here, you can see the legacy cryopackaging, which was used in conjunction with our 8-qubit processors as we developed and tested them at UC Berkeley. And so going forward for the AQT, these have been redesigned by Bleximo to improve electromagnetic hygiene, leading to a reduction in crosstalk as well as increased lifetimes. So for example, the high lifetimes that Ravi demonstrated in his slides were measured actually in these new boxes. So the new boxes are modular. They have PCBs that can accommodate quantum processors of different sizes, and they can be swapped out inside the same box. They're also extensible to 40 connectors per box to accommodate different cryopackaging will be the standard for the AQT going forward. And we've already used these, so these are deployed in our systems currently. And we're collaborating with Mohan Saravar of Sandia National Lab to conduct an experiment on characterizing the crosstalk mitigation results of so here, some more details regarding the improved electromagnetic hygiene. These were simulations conducted by Bleximo in designing the new cryopackaging. And so here you can see improved port matching better than 25 dB and crosstalk reduction better than negative 55 dB. So
you cut out at minus 55 dB, so maybe you want to repeat that last sentence.
Oh, I'm sorry. So yes, the negative 55 dB is for the nearest neighboring qubit lines, and then for other qubit lines, we have better than 72 dB reduction in crosstalk. At 10 millikelvin, and that is done in a Blue Force XLD series dilution fridge, which has 1,000 microwatts of cooling power at 100 millikelvin. And the experimental space under the bottom plate, where we have the 10 millikelvin, is also designed by Bleximo. And there are 160 RF lines that connect this cold stage through the fridge to the controls equipment at room temperature. And 16 of these lines are superconducting and include HEMT amplifiers for readout. And this fridge, this type of fridge, but this fridge in particular, is at the core of the AQT facility, and it has been operational for the last few months. But Advanced Quantum Testbed. So a bit more on the experimental stage. It is vertically divided into 3 parts, as you can see. Parametric amplifiers. The first stage of amplification that we have.
That's right. You're cutting out a few times. Maybe you want to sort of just turn off your video for the moment, and also sort of back up just a few bullet points.
I apologize. So here a bit more about the experimental cold stage. It is vertically divided into 3 parts. At the very top, we have the traveling wave parametric amplifiers, which is the first stage of the amplification coming out of the quantum processor. And these are divided into grouped and divided into groups of 4 2-pas and shielded from magnetic fields. Then the next stage under that, we have the control volume, which is, it consists of bracketry and bedboard plates for supporting and thermalizing microwave components. So these are things like filters, isolators, circulators, and the like. And then underneath, we have the sample volume, and this is where the cryopackaging sits inside shielding. Now, if you look at the cold stage horizontally, you'll see that the experimental space is compartmentalized into porters to support multiple experiments in parallel. And that is again hinting at the mode of operation of the Advanced Quantum Testbed facility, which is not necessarily to go after operating the largest quantum processor that we can and getting the last bit of performance out of it with the largest number of lines, but instead to investigate fundamental science and fundamental technologies that will help us guide the path to development of future groundbreaking technologies and future quantum processors. So a bit more on the electromagnetic shielding. Here you see an example of the shielding for the cryopackaging at the very bottom of the fridge. So these are tri-layer shields for the sample. The inner shield is superconducting niobium and is coated on the inside with electromagnetic absorbing material. It is surrounded by two shields made of mu metal. And here you see in simulation the effect of the combination of this shielding, which is a 50 dB reduction in magnetic field norm compared to the outside environment of the shield. For the two parts, the shielding is also very similar, but it is bilayer. So one niobium superconducting, again coated with electromagnetic absorbing material on the inside, surrounded by a single mu metal shield. Now, moving out of the fridge, as the signal passes between the room temperature controls instrument and the quantum processor in the fridge, it needs to be mixed and up-converted on the way in and down-converted on the way out. And traditionally, we've done this mixing through discrete components, such as mixers and amplifiers. But these are expensive and take up a lot of room. They're not very amenable to extensibility. And so to address this issue, members of our team at the Accelerator Technology and Applied Physics Division at LBL have developed standalone PCBs that incorporate and integrate all of those discrete components into a single PCB that can take care of all of the up or down conversion for a single RF line. And we've tested these to compare them with traditional RF chains, and we've seen that they perform equally as well. And these are now being deployed, and we have a set of them that is under use and testing currently for our new chips, for our new boxes. So the next step after the mixing of the signal is the controls hardware. Now for this, I'm going to start with the commercial solution. So these are provided by Zurich Instruments. And the setup consists of three types of devices. So first we have multiple high definition arbitrary wave generators for qubit control. And these operate at 2.4 gigasamples per second up to 750 megahertz. Then we have quantum analyzers for readout operating at 1.8 gigasamples per second up to 600 megahertz. And then we have a single box called a programmable quantum systems controller to synchronize the operation of all of the rest of these boxes and devices, which would then allow us to control tens of qubits in parallel. And the Zurich instrument setup also enables fast parameter change without the need to recompile and re-upload the full sequence, and also has the ability to perform state detection on the fly, which enables fast reset and fast feedback and fast reset with 400 to 700 nanoseconds point to point. And this system is also currently deployed, and we've been using it for the last few months, and is currently finishing integration into Qtril, which is the AQT's software control stack. Now, in addition, we would like to also be able to accommodate potential custom needs of our researchers and users. And so to that end, in Applied Physics Division, again, at Berkeley Lab, have developed the in-house control solution, which we call Qubic, standing for Qubit Control System. And so this system, a single chassis here, consists of an FPGA, 8 DACs, and 2 ADCs operating at a gigasample per second. The analog front end utilizes the same PCBs that I showed earlier, along with low noise local oscillators. And the system is very extensible and modular, so multiple units can be synchronized to drive larger qubit chips. Qubic accommodates arbitrary wave pulse sequence generation, and also allows for fast parameter change without the need to recompile and re-upload. It is also capable of signal decoding on the fly, which enables fast feedback and fast reset, as you see here on the bottom right. We have also demonstrated things like crosstalk compensation, and our team is also and we're using the system to develop single qubit.
Professor, you cut out at crosstalk compensation, so maybe repeat that sentence.
I'm sorry. Yes. Yes, we have demonstrated things like crosstalk compensation, and the team is also developing a graphical user interface to make the system easier to interact with for the users. And we're using this system to develop single qubit characterization and calibration protocols. And we hope that this will allow us to accommodate the needs of the researchers, the custom needs of the researchers and users of the AQT as they arise going forward. So this was an overview of the hardware involved in the AQT. But at the end of the day, our goal is to make it as seamless as possible to the end user to take advantage of all of our capabilities. And so we're doing everything internally so that to the external user, they can feel free to use the environment of their choice to generate their circuits and sequences. And as long as the final output is in the OpenChasm format, we'll be able to accommodate it. And so the process will be then to use tools such as Ticket to optimize the sequence and circuit, then transpile using our own in-house developed transpiler to make it compatible with our software stack Qtril, which will then interface with hardware such as Zurich Instruments, Qubic, or other options to run the experiment. And you'll hear more about the details of this in a later talk from Kostin, and I believe some interesting work on in Anna's talk as well later in this session. So with that, I would like to thank you for your attention, and if you have any questions, I'd be happy to discuss later.